Alright, welcome to our 17th video. This one's on electronegativity. So, electronegativity is defined as the ability of an atom in a molecule to attract electrons to itself. Okay? It's basically the ability to take new electrons. The greater an atom's electronegativity, the greater its ability to attract electrons to itself. Kind of a duh, but just make sure you got that. So the stronger the electronegativity, the higher the value, the stronger the attraction to new electrons. The electronegativity in an atom is related to the atom's ionization energy and electron affinity. We'll mention that a little bit later. But ionization energy, definitely know, which are properties of isolated atoms. So it's related basically to the trends that we've already talked about. An atom with a very high negative electron affinity and a very high ionization energy both attracts electrons from other atoms and resists having its own electrons attracted away. Now, ionization energy, electron affinity is basically like the opposite of ionization energy. So ionization energy is the energy required to lose an electron, and the electron affinity is the energy change resulting from gaining an electron. This means that basically, if we have a very negative electron affinity, so energy is released when we actually gain electrons, meaning it's very easy to happen as opposed to adding a lot of energy, and a very high ionization energy, meaning electrons are pulled very strongly to the nucleus, and it takes a lot of energy to release it, we have is highly electronegative. Basically, if electrons are held very if current electrons are highly attracted to the nucleus, new electrons will be as well. Okay, so it's like if you've got a magnet and you got a bunch of metal stuck to it, the stronger this stuff is stuck to it, meaning the stronger the magnet, the more easier it is to get more stuff stuck to it as well. So the stronger the pull, the stronger the nuclear charge, the higher the electronegativity, the stronger it is to pull more stuff in. So in general, there's an increase from left to right across a period. That is from the most metallic to the most non-metallic elements. Which basically also says that metals are going to have a very low electronegativity, like pathetically low. They typically form positive charges, and by typically I mean they pretty much always form positive charges. And nonmetals tend to form negative charges, meaning they tend to have high electronegativities and thus take atoms, or electrons. Wow, not atoms. With some exceptions, especially in the transition metals, electronegativity also decreases when going down a group. Think back to electron shielding. The bigger the actual atomic size, the less nuclear charge you feel on the outside. You've got electron shielding going on. And electronegativity deals with the charge electrons experience. So the lower that charge, the lower the electronegativity. As opposed to nonmetals, which are typically smaller and more concentrated, if you will. They have a higher nuclear charge on the electrons, thus they pull more electrons in. So periodic trends are very useful, though, when designing new molecules and materials. Because actually, when it comes down to it, replacing an element of one group with another in the same group typically gets you similar properties. Now, they're not identical, but basically all alkali metals act similarly, at least in some instances. All alkaline earth are very similar. So one of the biggest questions people ask is, why do we care about periodic trends? And especially when you get into the medical field and you realize that I've got this compound, but this is too expensive to make. Is there any other alternative? And you can start looking at trends and find atoms that are similar in various trends that you need, and thus you can find a couple replacements. They may not be as good as the original, but they're pretty close. For example, SiO2 can be a ceramic. Turns out actually SnO2, which is a couple rows down below it, can be as well. So just keep in mind that they have similar properties in the same group, not identical, but similar. Thus, they can oftentimes replace each other in certain cases. So lastly, let's rank the following elements by increasing electronegativity. sulfur, oxygen, neon, and aluminum. All right. Hopefully you've tried this. Sorry I didn't tell you to pause, but probably figured it out. We've got sulfur, aluminum, oxygen, and neon. Now, here's the interesting thing about non-noble gases. Noble gases typically have an electronegativity of 0. Like, not quite 0, but low, because they're not trying to attract new electrons. They're not. They're full. They're content. There's no reason. Dang it, I don't know that. Okay, so here's where it gets weird. Neon's a noble gas. Now, by all logical sense, neon should have a high electronegativity. Here's the thing. Well, the why is because it's a small atom, etc. Here's the thing. When you research this, a lot of people will say that neon has no electronegativity because it's a noble gas. If you ask them and say, well, what does that have to do with anything? Their response is, neon has a full octet, as all noble gases do, and so thus it has 8 electrons and it doesn't want more, so it doesn't have electronegativity. I'm sorry, that's stupid. Atoms aren't conscious. Atoms aren't living. Atoms don't think, oh, what's today? I think I want more electrons, so let me have a high electronegativity. No, they don't. So, interesting thing about neon, and that's partially why it's in here, is I need to kind of address this, is we, as of at least a couple years ago, I haven't actually checked much recent, we have no compounds in neon. And actually, the only way we calculate the common type of electronegativity we use is by comparing bond strengths in molecules formed with that atom. And actually, it turns out that there are some krypton compounds and xenon compounds, even though they're both noble gases, and they thus have electronegativities. Neon, however, we don't have data. It might be high, it might be low, we don't have data. So for neon and most noble gases, when dealing with electronegativity, basically they're not going to really factor in. You're just going to be able to ignore them. They're not going to really ask you questions about it, largely because the trend kind of falls when you get to noble gases, because some of them work, some of them don't. So typically fluorine, think of as your highest electronegativity, which is over here. So ranking these as increasing then is going to be aluminum, sulfur, oxygen. Again, noble gases, some of them have data, some of them don't. Neon, for example, we don't have data. So we can't really make a choice. While yes, it has a small size, it's just kind of weird. So we tend to ignore noble gases when electronegativity comes in handy. So with that finishes electronegativity. Thanks for watching.